Okay, so let's start the last session today. So I'm very happy to introduce to you David Lopez-Paz. So David did his PhD, I think, bridging, traveling a lot between Cambridge with Tübingen, Germany, and Tübingen with Bernd Schalker. And so he has worked on several very interesting topics, including something that we heard about during Arthur Breton's talk, detecting causal relationships. But I think that today he's going to tell us about how can you use randomness in machine learning across different settings. And the idea is that it's going to be a mix between tutorial style and practical style. So we'll have to, I think you'll have to coach a little bit. So please, David, go ahead. Oh yeah, I forgot to say that he's now at Facebook Research in Paris. Yes. Okay.
Cool, so I think they send you a list of imports from Python that should work in your machine, and we will be going through a Python notebook from scratch together in order to code the exercises. So I have a series of exercises. Some of them will be a little Python experiment, and some of them proving a little theorem, and for the theorem part we will do in the slides all together. And so the first thing that I would like to ask you is to go to this URL here. This is going to be a paste of code that I will be updating as we go. And right now it includes the imports and the URL to download the MNIST dataset. And also, I guess, to do this a bit more dynamic, you could work in pairs or in triplets. So if you're sitting alone, you should move, join someone else, and work together. Yeah? Sorry? No, the slides are not in the internet because otherwise you would have all the solutions. But after the tutorial, I will ship them. Okay, so in 1-2 minutes we start. So set up the notebook, import the stuff, download the dataset, and we're ready to go.
Do you recommend Python 2 or 3?
I'm using Python 2. Yeah. But I think it will work with 3. It's scikit to learn mostly. So. Okay, how many of you are set up already? Almost, okay, 30 seconds. So in the meanwhile, a bit of introduction perhaps. We will be talking about randomized algorithms, and these are algorithms that use some sort of randomness to make some decisions. Okay, so it's a very broad concept, but we will be focusing on things like numerical algebra, kernel methods, and so on. We will start super simple, like with a little simulation to compute some basic quantity, and then we will ramp up slowly. So hopefully there's material for all levels in the audience and for now. So let's start real simple, as I said. So the first experiment will be to build an atomic bomb. It looks like something like this. This is a picture from the Trinity test. It was taken in July 16th of 45, and from the floor to the top of the explosion here is 200 meters. Okay, so in order to build such a device, it was required to join forces with a lot of smart people and develop new methods to compute and simulate complex things like chain reactions in neutrons in fission devices. So in this picture you can see from left to right Johnny von Neumann, Richard Feynman, and Stanislav Ulam. And these three people were working on the Manhattan Project in order to build a gadget like the one shown in the previous slide, and they came up with this difficulty of evaluating very large-scale multidimensional integrals. Okay, so the problem they faced is evaluating a quantity of this sort where x is a vector. And Stanislav Ulam really liked to play cards, and he has an uncle that used to borrow money from his family to go and play and gamble to Monte Carlo. So when Stanislav Ulam was with his uncle in the casino, in order to compute the winning probability of playing the solitaire, instead of enumerating all the possibilities, he came up with the idea of just sampling configurations of the board and counting how many of the configurations were a winning move out of all the configurations that he sampled. And that was pretty much how the Monte Carlo method was born. Instead of evaluating all the possible inputs x, you're going to define a probability distribution over the input domain, p of x, and you're going to sample from it. You're going to sample, for example, n times from the probability distribution and evaluate this function at all those n locations and compute the average. Okay, so the first exercise will be to compute pi using a Monte Carlo simulation. This should take 2 lines of code in Python, and then we will analyze what's going on. So try to do that. And if you have any questions, just raise your hand and I will go there and help you. And if you finish doing it, just raise your hand as well so I can get a feeling of how fast the people is going. This should take like 5 minutes. Okay, so a little hint. If you have a square from 0 to 1 and from 0 to 1, and you draw a quarter of a circle in there, then by computing the ratio between the area of the quarter of a circle and the area of the square, you would get close to pi, right? It would be just pi times the constant. So let's see who does first blood. I just written there a line to sample from the unit square, and now we need to compare these random samples, n of them, against the area of the circle. So the condition to be in the area of a circle of unit radius is just that the square of the coordinate x plus the square of the coordinate y is less or equal than 1, right? So something like Okay, so something like that. We're approximating the integral by sampling at uniform numbers from the unit square. Then we're squaring those numbers, we are summing them, and for each of the rows that we will have in this vector, we will compare it if it's less or equal than 1, and then we will compute the average. And that will be pi divided by 4, because the area of the circle will be pi times r squared, r is 1, and since we need 4 times the area that we're computing here, because it's a quarter a circle, we multiply by 4. Okay, if we do 1,000 samples, it's not that good. And if we do 10,000, it gets better. And if we do 100,000, it gets a little bit better. So, yes. What's in the blue? Here?
Yeah.
This is less or equal? Less or equal?
Okay.
Yeah. Literally. Okay, good. So, of course, this is a stupid example, but the shocking fact here is that regardless of the dimensionality of the input domain, in this case x, in this case it's two-dimensional, x and y, but it could be a million dimensional, the speed of convergence of the Monte Carlo estimate to the true thing that we want to estimate will be the same rate. So does anyone know how the error of this estimate looks like with respect to the number of samples we draw? So the more samples you draw, the better your estimate will be, right? So do you know how fast does the error shrink as we sample more and more points? 1 over square root. And why is that? Central limit theorem, right? But this will be regardless of the dimensionality of the input, which is quite a remarkable fact. If you were to do a grid search, the dependence will be exponential in the number of dimensions. And then this 1 over square root of number of samples has a hidden factor in the numerator, which is the variance of the quantity that we want to estimate. So if the quantity that we want to estimate has a large variance, then it will be that variance divided by the square root of the number of samples. And we can check that pretty quickly, actually. If we do something like this. Okay, so here I'm just building an array of 10 positions where I will set the number of samples that I want to sample. Let's say 10, 100, 1,000, 10,000, etc. And then in P, I'm going to collect the relative error of the Monte Carlo estimate with respect to the true quantity that we want to estimate, in this case pi. I'm going to do 10 repetitions just for the sake of reducing a bit the variance of the randomness in the procedure, and then we will see the shape of this curve. Okay, since we are operating with very large difference in numbers, like 10 samples versus 10,000, we're going to plot things in log scale. And we get a line like that.
No. This,
Sorry?
looks like so.
Nothing?
Could you please draw it up?
Yeah, so I can actually share this piece. Okay, so it's in the paste. You can copy paste that. And this looks like a line, right? But it is a line because we're in the log scale. So if you have a 1 over the square root of t dependence, where t is the number of samples, you should have a line that decreases with slope 1/2. And more or less is what's happening here, right? For -7 you have 14, and for -4 you have 8. So there's a 1/2 dependence there. Any questions so far? So this was just like a really simple exercise to get a flavor of the things to come. Oh, yeah. It's tinyurl.com/randomized-practical. Okay, so any questions, or should we move to the second exercise? Yeah.
So can you put also the estimate pi?
The estimate pi.
Plus b?
Yeah.
Yeah, it's not included.
Yeah, so there you go. Okay, let's move on. So another remark for Monte Carlo is that it works very well, and actually it's the only strategy with guarantees for model selection. So if you have, let's say, a neural network that you want to train, and you have two parameters, for example, the number of layers and the number of hidden units in each of the layers, proceeding at random with respect to searching for values for these parameters will be most likely the best thing to do. In the sense that, imagine for example that the number of hidden units per layer doesn't matter in your problem, but the number of layers is an important parameter. Then, by sampling at random, you will try more values for the number of hidden layers than sampling in a grid, right? And this only gets worse in high dimensions. So if you have a high dimension grid exploration for your hyperparameters, then doing the very stupid thing that we have done for pi works wonders. Okay? And there's this little theorem called the rule of 59 that is not very well known, but I think it's very cute, which says that if you run 59 experiments of this sort, of sampling random parameters and evaluating the error, with 95% probability, you will have one of the top 5% models in the whole space of parameters with respect to that sampling scheme, right? And the proof is also one line. If you think about it, this probability, the probability of this guy being greater than alpha, only happens when each of these guys is greater than alpha. So it happens with 1 minus alpha to the t probability, right? And since we want the reverse inequality, well, the probability of this thing would be 1 minus alpha to the t. But the bottom line is that, surprisingly, something that looks stupid, which is to search for your parameters at random in an architecture of a neural network or so on, is actually the only strategy with non-guarantees. Right? And for more information, you have a reference that you can check it. Okay, enough Monte Carlo for now. Let's do a bit of numerical algebra. So I guess all of you are familiar with the singular value decomposition. Essentially, if you're given a path matrix, for example, the blue matrix here, and you know that the rank of this matrix is less than the number of columns n, then you can hope to decompose this matrix into a product of three matrices, where the first matrix has the same number of rows as the original matrix, but many fewer columns, in this case R, a diagonal matrix of R times R, and then another matrix which has n columns and then R rows, right? So this representation here is what we call the low rank representation of the matrix A, and of course it requires much less space to be stored and much less computation to be multiplied against. So the singular value decomposition is one of the most crucial operations in linear algebra. It's being used for low rank matrix approximation, of course, by PCA and many other very basic algorithms. Yes?
The quality of the text is a bit poor. I'm struggling in reading all the elements of the page.
Yeah, I can really push the resolution higher here. But, well, essentially the little text here is saying one example of what these things could be. Here they are exemplifying the matrix A to be words per row and hashtags per column. And then the singular value decomposition will give you a matrix U, which is the embedding of the hashtags. And then it will give you a matrix B, which is the embedding of the words.
What's the difference between truncated SVD and SVD, normal SVD?
So the normal SVD will compute, so a number of columns R equals to n. So it will find an orthogonal matrix U of m times n. So it will have the same number of columns than the original matrix. An n times n diagonal matrix and an n times r V matrix. So it is no longer a low rank approximation in the sense that if you multiply these three matrices together, you will get exactly the original matrix A. But truncated SVD, on the opposite, will not compute all these orthogonal columns and all these singular values. It will compute the top, it will compute just R of them, such that those are the R largest singular values and the associated columns and rows for these matrices. Yes?
Complexity of this is should be n times r.
So this is for the full rank SVD, right? So if you're forced to do the full SVD decomposition, the computational complexity will be linear in the number of rows and quadratic in the number of columns. So in this case, we have many more rows than columns. So it will be linear in the fat dimension and quadratic in the small dimension. But the interesting thing is that we can compute this decomposition much faster using random numbers, random vectors indeed. And it will work as follows. It will be 5 steps. The first step will be to compute a matrix Q such that Q is of dimension m times R plus B. Remember that R is the target rank that we want to approximate. So we want an R dimensional, so a low rank decomposition of order R. And P is just some oversampling parameter, right? Since the algorithm is going to be random, we will allow for a little bit of margin for the algorithm to correct its own errors. But the matrix Q, the bottom line is that it will have many less columns than n, right? If we can compute a matrix Q that satisfies this approximate equality here, what we're doing is to compute a matrix Q that approximates the action of A. In mathematical terms, Q is an approximation to the basis of the range of A. Essentially, if the number of columns of Q is n, any orthogonal matrix will satisfy this equation, because for any orthogonal matrix, Q times Q transpose is equal to the identity, and therefore you get A equal to A. But for a smaller amount of columns, you need to build some structure into Q, and this structure will be dependent on A, right? And we will explain in a minute how to do that. But assume for now that we have computed a matrix Q which has orthogonal columns and approximates the action of A such that this approximate equality holds. Then we're going to use Q to multiply against A and obtain a matrix B of R plus P rows and n columns. So this is already much smaller than the original matrix, because the original matrix had m rows, and now we have reduced the number of rows drastically to R plus P. Assume, for example, that R plus P is 10% of m. Then we're going to compute the SVD decomposition of this matrix B, the full one, with the normal method that is provided to you by LAPACK or any other linear algebra library. And the SVD of B will be S sigma B, and this will be computed in this time complexity. Number of rows, again, linear, and number of columns, quadratic. Then we're going to realize that A is going to be equal to Q times B, okay? And then if we write it down, we get, if we write instead of B, we write the singular value decomposition of B, we will get Q times S sigma V transpose. We're not going to compute that, this is just an observation. We're going to use this observation to construct a matrix U, which is Q times S, and then we're done, because Q times S will be the orthogonal matrix U, because Q is orthogonal, S is orthogonal. The matrix multiplication of orthogonal matrix gives you another orthogonal matrix, and then sigma and V we can just reuse from the previous SVD. Okay, so now the question is, how do we compute Q, this orthogonal matrix that approximates the shape of the range of A? And the answer is at random. What we're going to do is the following. We're going to sample a random matrix omega, and omega is going to have normal entries. So omega ij is going to be sampled from a Gaussian. And we're going to fill this matrix omega with numbers sampled from a Gaussian. Then we're going to multiply A times omega. Okay, and without going into any details, this multiplication, since omega is a random matrix, can be performed much faster than normal matrix multiply. But forget about that. Just assume that A times omega is very easy to compute. We do that and we get the matrix Y. Okay, so then we will compute the QR decomposition of Y. Now, where this will be given as a function in Python, we don't have to really understand what's going on. But essentially, the computational complexity here will be linear in the number of rows, as the original SVD decomposition, but quadratic in this little r plus p, not quadratic in n, right? So the savings are huge, actually. And this QR decomposition, if you don't know, is going to give you a product of two matrices, Q and R. Q is going to be an orthogonal matrix. Now, you see the link to the previous enumerate. And R is going to be an upper triangular matrix. We're going to disregard R, and we're going to return Q. Okay? And Q is n, so number of columns, times R plus P, which is this little rank that we have decided a priori. Okay, so the second exercise, it looks more complicated than it is, but it's to implement this in Python. Okay, so just try, and if you get stuck, if you have any questions, raise your hand. I can walk around and I'll give you hints. This one? Yeah. Okay, so the first step will be to compute the matrix Y. And this is quite easy, right? A, yeah? A is the argument. So you are given a matrix A, you are given a target rank R, and they ask you, please give me a truncated singular value decomposition of A of order R. Yeah, so the first step is quite easy, right? You just construct omega, which is mp.random.randn of dimensions m and r plus p, and you multiply it against A, and you get Y. So that should be pretty easy. I'm gonna be doing it quite slow here. Yeah. Yes, that is actually a problem. Yeah. And for those of you who are already a bit ahead, to compute the QR decomposition of a matrix in NumPy, you just do np.linalg, which is the linear algebra package, .qr. You place the matrix, and it returns two arguments, Q and R. Okay, so the type of festival has started, and I need to update this slide. Yeah. I mean, I guess you can figure out the dimensions by yourself, but omega, of course, has to have n rows because it's being right multiplied by 8. Yeah, sorry about that. So yeah, R is an argument of your function, and P is also an argument of your function. Or you can set P to R as well. It's just some small number to correct the randomness.
Let's say they have like 4.
Also, people is asking, why does the matrix omega, it's random, so why is it helping at all? Why can I construct Q randomly from the very beginning? And as you can see, omega is random, but it's being multiplied with A. So you can think of each of the rows in omega as one witness of what the matrix A is doing as a linear transformation to its inputs, right? So each row of omega is going to be a random vector drawn from a Gaussian, and it's going to reveal the directions preferred by the transformation given by A, right? So it's going to inform you about the eigenvectors, or the singular vectors of A. But since each row of omega is random, they will be independent from each other, and therefore these little pieces of information that you get from each of the vectors will be different, right? So it's going to give you some kind of witness about the action of A, but a different kind of witness. So that's more or less the intuition. Let's do the first lines altogether. So my SB. I'm given A and R. Okay. Sorry? The top half? What?
When you switch the orders.
Oh.
No, they want to shift. Oh, I see.
Yeah, but actually, I'm gonna do the bottom half first, right? So I think think you want the other way. Yeah, I guess I can. Okay. Just briefly go to the paste. I'm gonna put a link to the slides there. Okay, so it's now the last line. Anyway, now you have the slides, so I can go full screen with the notebook. I can stop like that until you don't know them. Okay, so let's build omega. I'm going to give r plus p equal to r. I mean, that would be fast enough. So the oversampling parameter for my function will just be r. If I want to compute 10 singular vectors, then I would have to build 20 rows. So this is my random matrix, quite simple. Now phi, as we said, is just the dot product of A and omega. And then you get the QR decomposition. Oh, yeah. And then you get the QR decomposition of Y. Okay? So everyone more or less on the same page, I think, here. Actually, we can drop R. We're not going to use it. Okay, so B is just the dot product of Q transpose times A. And then we've been told that we need to compute the singular value decomposition of B, which is going to be S sigma V. And it's just MP linear dot STD. Okay? Next is to compute U. Again, just a matrix multiply. And we're pretty much done. We could return U, sigma, and V, but since I'm going to plot some stuff, I'm going to drop already the columns that do not interest me, so I'm just going to keep the first R columns for U, for sigma, and for B. I used to call it K, so I'm putting K over. And then I'm going to return my low rank matrix. Usually you would like to return the decomposition itself, so that's U, sigma, and V separately, but I want to compare my result with the ground truth, so I'm going to return already the low rank approximation build-up. Q, sigma, and B. Okay, you have the slides, so I'm going to just put it here. Okay, let's see if this breaks. How to construct a low rank matrix. This is very simple. 100 rows, rank 10, dot product with something with 10 rows and 100 columns. So it's going to be squared. Okay? So the shape of A should be 100 times 100, but the rank of A is 10 because there's this bottleneck in the middle, right? Okay, my SVD 8 takes 2 arguments. So 10, this is cheating, we know the rank, we are just going to sanity check if everything is okay. When I'm going to subtract A, so A is rank 10, my SVD was given the order to compute rank 10, so the approximation should be almost exact. Let's compute the norm. And you get almost 0, right? Okay, so it seems to work. If you put less rank here, so for example 5, you're asking the algorithm to do something impossible, which is to approximate a rank 10 matrix with a 5 rank matrix, so things start to look more sketchy. Yes, this would be lossy compression. Okay, so I tried to convince you that this algorithm was faster from a computational point of view, so why not just check it out. So I will share this code now in the paste.
How do you check it? So what was the last test you made?
Oh, so I computed the rank 10 approximation of A, right? So I built a matrix which approximates A but only has rank 10. I subtracted A from it, and then I should get a matrix of very little numbers, which are the residuals of my SVD decomposition. If I compute the norm of this matrix, then I am expected to get a very small number, which is the precision of my SVD routine. Right, so we're only considering 10, and we know the rank is 10, so this is a sanity check that things are exact up to the numerical position. Okay, so I'm going to share just a little routine to plot stuff. Okay, so if you go to the paste, you will find here 2 SVD and a bunch of code. It contains both my SVD implementation and the code that I'm going to show you now to validate its performance. Okay. Okay, so from the beginning, this is my routine, my SVD. This is what we just saw, what we implemented. And now the only thing that I'm going to do is to construct matrices of different sizes, 100 times 100, 200 times 200, and increasing. And I'm going to measure 2 things. I'm going to measure how long does my SVD routine take to execute on increasingly large matrices. And I'm going to also measure the error of the solution, right? And I'm going to measure these 2 things for 3 different algorithms. Normal SVD, which is the one that doesn't use randomness. I'm going to measure the same quantities for the randomized implementation of Python, that is like the pro version of my SVD. And I'm going to measure also my implementation and see how they rank. Okay, so my SVD, of course, is my implementation. Randomized is the implementation of this same randomized algorithm by the NumPy library. And RPAC is the old-fashioned way of doing truncated SVD. Yeah.
I think this is the fastest way to compute the SVD.
If it's the fastest. Yeah, it works wonders. So every time you call truncated SVD on a numerical linear algebra routine, it's doing this. Okay. Let's see what we get. Okay, so this is running on matrices of sizes 125 to 2000. And the rank of each of the matrices is just 10% of the size.
So are there actually algorithms that compute only the rank U and like rank approximation of U and V without like computing the whole SVD to make it faster?
A log rank approximation
Yes.
of U and V. That is pretty much all you need to do, right? The only difference is segment there. If you only want to compute the rank of the matrix,
No, I question like when we compute SVD, like truncated SVD, can we compute it without like computing actually the whole SVD and then cut it?
oh yeah. So actually, that's what the NumPy implementation is doing. Yeah.
Oh, okay. So
Yeah.
it's not computing the whole SVD.
No, it's just computing the top R comments from Okay, so this is what we get. Laidback is the old school implementation, and this is running time, so it quickly explodes actually. And then both the blue and the red lines are the randomized version of SVD. The red line is Python's implementation, so, well, I think it's scikit-learn implementation, sorry. So it's supposed to be highly tuned and reviewed by people. And the blue line is my beautiful creation that we did all together here. And they are pretty much on par in terms of running time, right? So it's quite remarkable that with 10 lines of code, we have replaced this green line that used to be what people used to perform SVD for decades, right? And in terms of error, which is on the right side, they are pretty much all of them exact, right? So you could say, oh, because you're using randomness, your solution would be not as precise as the true thing, but indeed the error is just...
So why Navak is still using the old fashioned way of the SVD?
No, it's not using it actually. If you call truncated SVD, the default argument will be randomized. Right? So by default, it's performing the randomized version of it. I set it here manually to RPAC such that we could see the difference. Any questions?
What was the difference between the two?
Sorry?
What was the difference between the two?
The difference between what?
The randomized and the
Oh, Laidback is doing, I think it's householder transformations, which is a variation of the power method to compute the largest singular value on the associated eigenvectors, and then condition on that the second one, and so on. Yeah. Okay, good. Any more questions about SVD? Yes.
Can you tell why multiplying around the Gaussian can be done efficiently?
Yeah, so what we are doing here is just naive multiplication between the random matrix and A. So it's going to be as slow as a normal multiply. But if you were to get fancy, then you would use things like fast Walsh Hadamard transforms, which are some sort of Fourier transforms on the discrete domain. And these, instead of taking linear time, they take log linear time. So instead of square time, they get log linear time.
Is this related with the article at ICML this year about doing multiplication with the Gaussian even more efficiently?
I don't know that paper. You're faster than me.
That's the answer.
This is related to, for example, the fast food paper, which was in ICML a couple of years ago, to do randomized kernel expansions, that we will do now. They were using those kind of matrices. Okay, good. So yeah, the SVD, perhaps the main application in machine learning is to compute the principal components of a matrix, which is used to do dimensionality reduction. Right. Okay, and now we will dive into a more brute force solution to the dimensionality reduction method, and it's to perform what can sound stupid, but it's actually very efficient, is to reduce the dimensionality of your data using a random projection. So the setup is as follows. You have some data, x1 and x2, and this data lives in a high-dimensional space, for example, images of high resolution, and then you're going to construct a random matrix which has the number of rows equal to the dimension of your data, and then the number of columns equal to some small number. And by multiplying your data with this random matrix, you will get a reduced a data of reduced dimension, in this case 100 dimensions versus the original space of 40,000, such that the distances between points are going to be preserved. So if you had a distance of delta between the image x1 and x2, by performing dimensionality reduction by random projection, you will get a couple of data points y1 and y2, such that the distance will be delta up to a very small number epsilon, right? So, for example, this is extremely helpful if you want to do nearest neighbor search. If you want to do nearest neighbor search in high-dimensional spaces, this is very costly because you need to, well, compute distances between high-dimensional points. So one alternative would be to multiply these high-dimensional points against a random matrix and then compare the distances in the low-dimensional space. Okay, and this result is formalized by the Johnson-Lindenstrauss lemma. And I think the proof is actually quite beautiful, and I will walk through it rather slowly. And if you have any questions, you can raise your hand. But it's just to give you a bit of intuition of how these things are proven. We will need two auxiliary lemmas. Okay, so these you can consider as independent results that will be little pieces of the main result that we will prove later. And the auxiliary lemma says as follows. Let Q be a random variable following a chi-square distribution with k degrees of freedom. Okay, you don't need to know what is this yet. Then, for any epsilon between 0 and 1/2, the following will hold. And that is that the probability of Q being sandwiched between 1 minus epsilon k and 1 plus epsilon k is going to be lower bounded by 1 minus 2 exponential of something. Okay? So if you give me a random variable Q, which follows this distribution, with very high probability, the value of Q will be sandwiched between these two values. Okay? So the proof starts using Markov's inequality. How many of you know Markov's inequality? Good. So Markov's inequality is essentially saying, well, for a positive random variable, the probability of this random variable exceeding some value A is less or equal than its expectation divided by this value A. Okay, so let's try to use it. We're going to try to prove only this part of the sandwich, and then the second part will be analogous. So the first step will be to do some massage to the inequality. And in particular, we will apply an increasing transformation to both sides of the inequality. By doing this, we are not modifying the probability at all, right? So the probability of this inequality is exactly the same as the probability of this inequality. Because all I did is to apply a monotone transformation to both sides of it. In this case, exponential lambda, right? Then I can apply Markov's inequality. And that is to apply this expression here to this exponential here. So I get the expected value of this exponential divided by this value here. And does anyone know what this expression corresponds to? It's the moment generating function of the random variable Q, which, for a chi-square distribution with k degrees of freedom, has this form. Okay, so far, I've just taken the inequality that I want to prove, exponentiated with a free parameter lambda, apply the MGF formula of the chi-square distribution, and we get this upper bound. Next, I'm going to tighten the upper bound, right? Because I exponentiated with a free parameter lambda, so lambda can be anything, any positive number. And if it turns out that if you want to make this inequality here as tight as possible by playing with lambda, then the value that you should choose for lambda is epsilon over 2, 1 plus epsilon. Okay? So these are tricks that are very well known. You need to know them in advance, but when you have the freedom of introducing one free parameter, one upper bound and stuff, then at some point you might want to tighten up the inequality by choosing a particular value for this parameter. Okay, if you choose this particular value, you will get that the probability that we want to upper bound is less or equal than 1 plus epsilon over the exponential of epsilon to the power of k divided by 2. Super ugly expression. And this is not quite there because the upper bound, the lower bound that we're looking for, has an exponential form, right? And this one doesn't. So then you have to invoke another trick, which is that you can upper bound these linear functions with an exponential function, right? So we have something of the sort 1 plus epsilon here, and it turns out that 1 plus epsilon is upper bounded by this exponential form, also an epsilon. So if you do that, then you get the upper bound of the probability that we are interested in an exponential form. And if you do union bound with respect to the other part of the sandwich, then you get the result. Okay, so a very technical lemma for those of you more mathematically inclined. I think it's beautiful to see how these things are obtained. And a second auxiliary lemma will prove the following. Let X be an n-dimensional vector, okay? And let A be the matrix that we will use to project this n-dimensional vector to the low-dimensional K, to the k-dimensional space, where K is much less than n. And let the entries of A be drawn from a Gaussian, okay? So this is already in the final thing that we want to prove. If we have a high-dimensional vector X, and we have a random matrix A, if we do the projection A times X, we will not modify the distances between points too much. So the lemma says that the squared norm of this projection is going to be sandwiched very tightly by the norm of the input vector X, okay, up to a margin of epsilon. How do you prove that? It is actually quite easy. You want to construct the result of the projections as x hat and compute the first two moments of x hat. The expectation is 0, because if you do the multiplication against A, all the entries of A are independent from X, and the expected value of A is 0, so everything gets 0. And the variance of X is a bit more involved to compute, but you just have to realize that the square of this sum, the only terms that will survive are the diagonal terms. All the cross terms that you will get if you do the full expansion of this square will be cancelled out, also because the expected value of A is 0 and independent from X. So you are left with this, which is just the product of the variances of A and X. The variance of A is going to be 1, so you are just left with the norm of X. Okay? And now we're going to reuse the previous result, right? Because so far I've talked about a distribution, a chi-square distribution with k degrees of freedom. How does this play a role here? Well, we have just shown that the result of the projections has a Gaussian distribution, the result of each of the coordinates. Actually, the jth coordinate of the projection divided by the norm of the input vector follows a Gaussian distribution. Then, if we sum all the coordinates, all the k coordinates, we will get a random variable which is the sum of k squared normals. And this is a chi-square distribution of k degrees of freedom. Okay, so let's use that lemma. This is the thing that we want to prove. So we will just apply the transformation AX to get x hat. Okay, and we take the k out of the norm, out of the square norm. And then this expression here, the norm of x hat squared divided by the norm of x squared, is going to be that sum of squared normal random variables, which is going to be the chi-squared random variable. And this is exactly the previous lemma, right, which was sandwiching the value of this chi-squared random variable. So in the end, you get this exponential concentration of the random projections. And the last step is just to apply these two lemmas together in order to get this result, but for a collection of data points, right? This was only for a data point x. If you apply union bound over all possible x's in a data set, you get the final result. And as a side note, you prove that this projection exists by proving that the probability of this projection existing is greater than 0, which is known as the probabilistic method. Okay, so this was a mathematical detour. Let's get back to the exercise, which is to empirically validate this inequality, which is you will load the MNIST dataset, you will project the MNIST dataset using a random matrix to some small dimension, and you will see that the distances are preserved. Okay? Yeah.
So I guess you can't just project it into like a one-dimensional space. I mean, there must be some kind of correlation between the dimension of the space and the epsilon.
Yeah, so k has to be at least this logarithmic term in terms of the data points that you have in order for the guarantee to hold. But let's try to see empirically what happens as the number of projections increases, and you will see that the estimate gets sharper and sharper. So let's do this one together. Okay, so you should have the MNIST loaded because of the first block of inputs that we did, but I'm going to load it again here. And then we're going to start. Okay, so the MNIST dataset is a bit large for doing a quick experiment here, so I'm going to subsample 2 sets of it of 1,000 points. Okay, so these are 2 random subsets of the MNIST dataset of 1,000 points each. And we're going to project them to a random subspace and see how the distances between the 2 subsets remain invariant or not. In order to do so, we have to compute the distances in the original domain, so let's do that. It's distances in X. We have imported pairwise distances. And let's do it between the second set, between the elements of the second set. And Ravel is just to convert the matrix into a vector. I just want statistics of the distances. I don't care about the distribution of the matrix. Okay, so I have computed all the pairwise distances between the second set of random points from MNIST in the original space. Let's do the same thing in the low-dimensional random space. For that, we need a random projection matrix, which is going to be just. So I'm going to use the first, well, the random version doesn't matter. So it's just going to be a matrix A, which a number of rows equals to the dimensionality of the data, number of columns equals to k, and then we need to divide by the square root of k, right? So this formula here is just constructing this matrix here. Okay, so 1 over the square root of k, and then A is just a bunch of Gaussian random numbers. Alright, we need. Should we project it down to 20 dimensions? Okay. So pairwise distances gets a set and another set, and then computes the distances between all the points in each of the sets. So if x2 has 100 elements, it's going to return a 100 times 100 matrix with all the pairwise distances. And I just want a vector, so I just flatten it with. So, yeah. So the pairwise distance is doing the Euclidean distance, I believe. Yeah, so we can do the square Euclidean distance. If you take the square root of everything, it will just work. It's fine.
Do you want the distance between x1 and x2? Yeah, that
I don't care, but I'm doing between x2 and x2 because then I will use PCA to do the same thing and compare with the random projection. And PCA will be learned on x1 and tested on x2, right? So x2 is our test set, right? And since the random projection doesn't learn from data, I don't need to use x1 so far. I will use it later. So Ravel takes a matrix and it flattens it as a vector. Yeah. You have a problem with this? Yes? Which is the problem? Okay, so next step is just to multiply stuff, right? Let's call the reduced dimensionality set space Z. So Z1 is going to be just MP dot of x1A, and Z2 is going to be MP dot x2A, and the distances between all these guys will be dz, which is again pairwise distances, but it's going to be between Z2 and Z2. I'm going to flatten this out too. Yeah. Sorry, I have to speak louder. Well, because the Johnson-Lindenstraus lemma uses the square of the Euclidean distance, and pairwise distances is computing the Euclidean distance. Yeah. Actually, I should square both. Sorry, I squared the matrix. This is not. You need to square the distance. Okay, so the theorem is saying that the distances will be more or less equivalent, so the ratio between the distances will live in this small margin epsilon. Let's just check that, which is to divide all the distances in the Z space by all the distances in the X space. Some of the distances in the X space will be 0, so let's add a little number to avoid numerical issues. And let's plot the histogram of this. So could you follow? Do you get a nice Gaussian kind of shape like this? Yeah. All good? Any questions? Something not working? Yeah.
Pairwise distance does, and why you choose both of the times x2 and z2 the same.
Okay, so pairwise distances gets two sets, x and y, and it will compute the distance between all the elements in x and all the elements in y. It's like computing the linear kernel matrix, if you remember the lecture from Apple. Okay.
So if both are the same, you will not
Both are the same, right? So the diagonal will be 0, because the distance between the ith element of x2 and the ith element of x2 is the same element, so it will be 0, but all the ij's, which are different, will have a different distance. Okay, so the bottom line is that you get, so this is the histogram of the ratios between the distances on the z space and the distances in the x space, right? And if the Johnson-Lindström lemma is correct, these ratios should concentrate around 1. And if you increase the amount of random projections, the variance of this bell shape should shrink as well, right? And if it shrinks around 1, it means that all the pairwise distances are more or less preserved. So even if you projected an MNIST dataset to a random subspace of 20 dimensions, you get quite a nice result, right? So most of the mass of this histogram is around 1, which means that the pairwise distance between those points is exactly the same. If you set k to be higher, then this thing should shrink, right? So I think it would be better if we plot it separately. So let's do a little loop here. Okay, so here I'm just looping over 4 configurations. I'm going to do 4 plots. 10 random projections, 50 random projections, 100 and 200.
Plus equals. Plus equals.
Oh yeah, sorry. Plot is not defined. No, it's not actually. Okay, let's do that a bit bigger, right? Okay, so, well, this doesn't fit very well. Okay, so this is pretty much revealing also about the MNIST dataset. With only 10 random projections, you can get a pretty good result, and it seems that if you increase the amount of random projections, things do not get that much better, right? So when you do 100 random projections, you are pretty much preserving all the pairwise distances. It's concentrated around 1, it goes a bit to 0.8, 1.2, and so on, and with 200 projections, it's really, really sharp. Yeah?
What's the original dimension?
MNIST is 28 times 28, 784 or something. And perhaps you're wondering, what if I use PCA? Right? Because PCA, it's actually targeting and minimizing this. So it's spending time on training data to find the optimal linear transformation that minimizes the variance of these histograms. So it should be much better. Okay, let's try that out. I think we have imported randomized PCA, which is PCA using the randomized SVD that we coded before. Yeah, so PCA, yeah, we're gonna do it inside the loop. So this is the stuff of random projections, and then PCA, any components, it's gonna be K, and then PCA.feed. So now we feed it on X1, right? That's our training data. So we feed PCA on X1, and then we transform the second set. And then we compute the pairwise distances. So I'm calling this the P space. Okay, that's it. And then I want to plot both next to each other. Yep. Let me copy the whole thing. Okay, done. And this thing finished already. And indeed, PCA is tough competition, right? With few projections, something funny happens. All the pairwise distances are underestimated, so this peak is not concentrated around 1, it's concentrated around 0.5. Does anyone know why is this happening? So this is an overfitting effect to x1. PCA, the transformation is trained on x1, so like any other learning algorithm may overfit. And this is indeed what is happening here, as you can see. But as you increase the number of principal components, yeah, it's quite difficult to beat, right? The concentration around 1 for 200 principal components, it's much greater than the concentration of the random projection. But still, I mean, if you decide to use random projections, you can use them online, right? As your data comes, you can just multiply it against random projection and do whatever you need with it. With PCA, you need a data set, you need to fit it there, and so on. And also, the random projection, you don't need to store in memory. Since those are random numbers, you can regenerate it on the fly. Okay, so any questions about this little experiment? Okay, so let's move to the next thing, which is moving into the nonlinear world of kernels. Okay, so you have this lecture by Arthur Gretton on kernel methods, and by now you know that kernels are these functions that receive 2 arguments, 2 data points, and they compute the distance of these data points in some high-dimensional hidden representation, right? So the kernel evaluation of x and x prime is going to compute the inner product between phi of x and phi of x prime, where phi is a mapping from the original space to the reproducing kernel Hilbert space of that particular kernel, right? But the particular shape of phi, we don't know. It's implicitly computed. So if you want to use kernels, the predictor that you obtain is going to be of this shape. It's going to be a linear combination of n kernel evaluations, right? So n here is the number of data points. So if your data set is large, a naive application of a kernel method will give you a function that is very expensive to train and very expensive to test. So now we will leverage randomness to compute an approximate randomized representation of phi that can be used to speed up all these methods. So this is what I said before. If you use kernel methods, you have to build this monstrous n times n matrix. Imagine you have 1,000,000 data points. This is completely infeasible. Moreover, you have to invert it. What can we do to approximate this guy? Okay, so we will be using a theorem called Mercer's theorem. And Mercer's theorem says that under some mild technical assumptions that we don't have to make precise for now, the kernel K will admit this representation here, which is an infinite sum of some basis functions phi and some eigenvalues lambda. Okay? So for example, the Gaussian kernel admits this representation. So under the hood, when you do kernel of x and x prime, what the kernel is doing is to compute this infinite sum, which is the dot product between these basis functions applied to each of the 2 data points, and then scaled by this eigenvalue. So the crucial observation here is that this expression here can be recasted as an expectation, right? So if we assume that the sum of the absolute values of all the eigenvalues is finite, then we can express this infinite sum as this expectation here, right? Where the L1 norm of lambda is just the sum of lambda 1, lambda 2, the absolute value of lambda 1, lambda 2, and so on. And since we have the kernel casted as an expectation, what we can do now is to sample the expectation, right? We can take m samples from this expectation, and this will be an m-dimensional approximation to the feature map of the kernel. But the problem is, what are the expressions for phi, right? So phi lambda, how does it look like? Because if I don't know an analytic form for it, I cannot sample them, I cannot use it. So it turns out that for some kernels, like the Gaussian kernel, in particular for the shift invariant kernels, this basis is the Fourier basis. Okay, and what does this mean? So a shift invariant kernel is a kernel that you can write with only one argument. This argument being the distance between the 2 points that you are evaluating. So k of x and x prime, if your kernel is shift invariant, you will be able to just express as k of x minus x prime. Okay, just as a function of the distance between the 2 points. These are the so-called shift invariant kernels, and they allow a Mercer expansion where the bases are the Fourier bases. So in mathematical terms, this means that my kernel, the evaluation of my kernel at these 2 data points will be the integral over these complex sinusoids here, weighted by some probability distribution p of omega. Okay? So, of course, we've talked about Monte Carlo, so we can just apply Monte Carlo here and see if we can get a finite dimensional expansion of the kernel to be used later for learning. Okay, in order to do so, we will first massage a bit this expression here and assume, for example, that my kernel is real. So if the kernel is a real valued function, like for example the Gaussian kernel, then we can work with cosines instead of complex sinusoids. And by applying some trigonometrical inequality, we can break the part of the cosines on x and the part of the cosines on x prime. Okay? And now we are ready to sample this probability distribution here, for example, m times, to get the dot product between m random frequencies on x and m random frequencies on x prime. But the bottom line here is that this will be the inner product on some m-dimensional space between some function that I call z applied on x and the same function z applied on x prime. So we are no longer doing dot products on some hidden infinite dimensional representation of the kernel function. We're doing it instead on some explicit finite dimensional representation that we have obtained by sampling the spectrum of the kernel. The bottom line is that if your kernel is shift invariant, you will be able to construct a map z of x, which is just a vector of cosines, where each of the cosines has a random frequency omega, and omega is being sampled from a distribution. So for the Gaussian kernel, and surprisingly, this distribution is the Gaussian distribution. So if you want to build a kernel machine on a large amount of data without building your kernel matrix, one thing that you can do is to build this feature map, which is just a random of, it's just a bunch of random cosines, right? Okay, so I propose to do that in code, which is to compute this expression here. So let's call these random features. And I'm gonna have the signature for the function. D is the dimensionality of my data, K is the number of random features that I will sample from the distribution, and gamma is the Gaussian kernel hyperparameter. And this will return a function, such that then I can take my data and transform it with the random features. So for example, random features dimension, a gamma, it's going to be Z of RFX. Sorry? Yeah. So again, if we want to approximate the Gaussian kernel, we need to sample from a Gaussian with 0 mean and variance 2 gamma, and B is going to be sampled from the uniform distribution from 0 to 2 pi.
Sorry, can I ask about your invitation? So, you've given an expression for Z. You actually want to explicitly create the feature vector for the kernel.
So I'm returning a function.
No, I meant just like on the slide.
Oh yeah.
So highlighted in red.
Yes.
So you're giving an expression for Z, which is, I guess, the feature.
Yeah. So it's RF. So Z of X in the slides will be RF of X in the code. I mean, we can call it Z if you want.
No, I'm missing something 3 steps back. So the point is, I think, to avoid having to calculate the ground issue, right?
Yeah.
But having this alternative representation of feature vector, how does that help you not calculate the ground issue?
You're just going to have. So when you have the exact kernel methods, you have to solve a dual optimization problem, and this involves computing the kernel metrics and solving that. But having this explicit representation will bring you back to the primal optimization problem, and those features Z of X will be your explicit features, and you will solve least squares, for example, of those features, right? So there's no matrix building or anything. You will need to build in many situations the covariance matrix of Z. But if you have 1 million data points and if you have 1,000 random features, then this is going to be 1,000 times 1,000, not 1 million times 1 million, right? Okay, so let's sample the parameters. Okay, so we need dk, right? Because we're going to multiply W with X. X lives in a d-dimensional space. We want k random features, so v rows, k columns, and multiply by the square root of 2 times gamma. Because the variance is going to be 2 gamma, so if you want that variance, you need to multiply by the square root of that. So square root of 2 times gamma.
So I'm also confused. So do we want to estimate the whole matrix K, or we want to estimate just 1/3?
No. So this function random features is going to return a function that featureizes explicitly one data point, right? One m-list digit into 1,000 dimensional vector features. And then you do that for the whole dataset, and then you build a logistic regression on this thing. Right?
So these features will be the same for all the points?
These features will be the same for all the points, and that's why I'm building this matrix W here, and then I'm going to return a function that will have it inside and apply to every data point. I also need to build this vector B, which is 2 times np dot 5 b random k, so it's just k uniform random numbers between 0 and 2 pi. is just this thing here. And then using these parameters here, I'm gonna just do the dot product between x and w plus b, mp dot cosine. Then I'm gonna multiply by this scaling factor. For the Gaussian kernel, by the way, ck is 1, because the Fourier transform of the Gaussian kernel is a Gaussian distribution directly normalized for you. So ck, this constant is gonna be 1 here. So it's mp squared 2 divided by k times that. And my function is going to return that. Okay. No, that is a typo in the slide. Good catch. Okay, so I'm returning a function that when I apply it, will return the featureization of some point x. I'm going to load the MNIST dataset again, just to have it around.
Sorry. Can you say again what was the type?
Yeah, the typo was here because the dot product gets 2 over n factor, right, here. So then if I break it into 2 pieces, into 2 multiplicative pieces, then the factor for each of the 2 pieces will be the square root of this. So that is the square root of 2 divided by square root of n. And here I have a 2. So it's square root of 2 here. Yeah. Okay. So, okay, I coded my random feature stuff here, and then I loaded the MNIST dataset. It's pickled in such a way that you can extract it like this, which is the inputs for the training, outputs for the training, same for validation, same for test. So I'm just gonna do the featureization for the training set. Actually, I'm gonna get a small subset again. So x1 is going to be okay, just 100 points for the sake of time, and then featureize it. Okay. So now, what's the shape of Z1 going to be? Yeah. So I decided to do 1,024 random features, and I collected 100 points. So my featureization is 100 data points of 1,024 features. Right? So now I can apply a linear method to this data set. I don't need to construct a random matrix here anymore. But just for the sake of exploration, let's see how well do these random features approximate the true kernel matrix. Okay. First of all, I'm going to share this with you. Okay, and then let's do a quick comparison of what's going on here. For that, we need the true thing, and the true thing is imported already. It's RDF kernel. So the true kernel matrix K is going to be our DF kernel of x1, x1, gamma 0.01. This is a value that I searched for, which works well. And then let's plot this matrix with image show. And it looks like that, right? And now let's do a random feature approximation and plot that as well. Let's just start small, so 100 random features. And construct my k hat matrix. Okay, so this is going to be the dot product between this primary representation. It's going to be the dot product between Z1 and itself, transpose. Let's show it. Let's put in the title the amount of random features that we use. Okay, so there's some resemblance. It's not exact, but you're only using a bunch of 100 random numbers to approximate the thing, so it's not that bad. Let's see what happens if we use more features. Oops. So let's do 4 then. So 4, 2 times 2 plots. And then another one with 10,000. It's too small. Okay, so here we go. So the exact is looking actually pretty close to the 10,000 random feature one. So, of course, sorry?
So are the values scaled on the same ranges? I mean,
Yeah. So, you mean the plot? Yeah, I guess probably, but I don't remember the command to scale them now. But the bottom line here is that you don't need to build these matrices, okay? This is just for the sake of illustration. If you were to use random features, you would just build your random features and use a linear method on it, like least squares, logistic regression, linear SVM, and so on. And if you do this sort of thing with 4,000 random features on the MNIST dataset, you get something like 98.5 test accuracy with a linear SVM on top of these random features. And this is tuning almost nothing, right? Nothing is chosen, nothing is learned or tuned. Just the bandwidth of the kernel, you hit run, and in less than a minute you get the solution for the MNIST, which is, of course, not state of the art, like crazy papers coming out that improve 0.1, but it gives you a flavor that these things can do a very good job with very, very little effort. Just 5 lines of code. Okay, and I think we can do a couple of examples more to see how can you use these random features, and we're free to go. We could use them for classification and regression, but I think that's rather boring. So let's do the thing we did before with PCA. We're going to take MNIST, we're going to do approximate kernel PCA to compress it, and then we're going to blow it up again to the original space and see if our digits look good or not. So, yeah, we will have all the code available later. Okay, so let's do it then. You can clear your mind. New section, approximate kernel PCA. Okay. So we will need the MNIST dataset again. We will need our random feature beautiful function. And we will start by converting the MNIST dataset into this random feature representation. So we build random features of the dimensionality for dataset. Let's get 2,000 of them. And gamma, again, uses magic number for MNIST. Okay, so we can featureize both the training data and the test data. Okay. And now ZTR is going to be 50,000 digits, each of them of 2,048 dimensions. So now we can take randomized PCA, which is a linear method, and perform it on top of these random features. Since the random features are approximating the reproducing kernel Hilbert space of the kernel, doing linear PCA on these random features will approximate kernel PCA on the kernel. But kernel PCA already in this dataset is unfeasible because you would have to build and invert a 50,000 times 50,000 matrix. And here the matrix that randomized PCA is going to have to internally invert is going to be 2,000 times 2,000, the number of random features. So let's build 20 components. Okay, let's compress this 2,000 dimensional randomized space into 20 numbers. Let's compress each of the digits into 20 numbers. So we fit it on the training data. I don't know how much this is going to get. Okay. And we transform the test data. So, well, let's transform both because we will use it. So PTR will be the principal component space. So PCA transform set TR, and PTE is the test. Okay, so now I'm going to send this to you so we can be on the same page. We don't need that. And I will wait for a minute and answer any questions that you may have. Okay, there you go. Are there any questions about PCA, kernels, features?
How does this relate to Nystrom?
To Nystrom? So in the Nystrom method, you select random rows and columns from the kernel matrix to construct a low-rank approximation, and then you orthogonalize it, right? So the feature map for the Nystrom method will be something like a matrix M to the -1/2, so the inverse square root of a matrix M of size n times m, which is the number of random features that you want, and then the kernel evaluation at m data points from your data. So as opposed to the random features, the Nystrom method is data dependent, so it adjusts a bit to the geometry of the data because each of the features is an evaluation of the kernel at a data point. But you need to invert this matrix M, right? And every time you need to test a new point, you need to multiply against this matrix M. So if you have 2,000 random features, this is already quite an issue. Yeah, you need to construct this 2,000 times 2,000 matrix, invert it, and every time a test point comes in, you need to multiply against this matrix. The random features in opposition, they are more agnostic, they are more independent to the data, so you might need more of them, but you don't need to build this organization basis anymore. Yeah.
So this assumes we have an exponential kernel which has a Fourier transforms.
Yes.
So which are the other kernels and transforms where we can use this trick?
So for instance, you can use the Laplace kernel, that could be something from a Monte process or from a Cauchy distribution. Finally, the arc cosine kernel, which is a kernel that people don't use that much. The arc cosine kernel, it's a neural network with an infinite amount of hidden units with the rectifier linear unit transformation. So it's max of wtx, 0, where w is sampled from a Gaussian. And there are many more. There's a table in a paper in CPPR 2014. I can add it to the slides. And the cool thing about this is that you could sample these random features with Gaussian with the width of the Gaussian kernel 0.01, but you could also sample with 0.1, 1, 10, and concatenate all of them together, and that would be similar to multiple kernel learning, and that works extremely well in practice actually. Okay, so let's continue. Recap: we have two matrices now, which are PTR and PTE. PTR are the 20 top principal components of the random features. Okay, so we have taken our data, the digits, map it into a random feature space, and that random feature space, we have taken the 20 top principal components. Now we live in a 20-dimensional space, and we want to go back to the pixel space to see if our reconstructions look good or not. So we just do regression, right? So we take a least squares regressor, so for example, so from PTR to XTR. Remember that PTR is the principal component space, and XTR is the original pixel space. So we're doing, 784 regressions from the principal component space. Okay, get it? Okay, that was fast. And then X hat TR, for example, will be the reconstruction of the principal components in the training data. Actually, we don't need this, we want to test it on the test set, so XTE, predict PTE. Okay, so XHTE should be living in the linear dimension, so it's actually 10,000 digits living on the 28 times 28 pixel space. And to plug them, I have some function here.
Can you go back a second?
Yeah, sorry?
Can you go back a second? I don't understand why you need to do regression.
Yeah, so we have compressed the digits into 20-dimensional space, and now we want to reconstruct it. So what we're actually doing here is an autoencoder without gradient descent, just encoding with random features and recoding with random features.
You have all the random features, you have all the principal components. Can you go back exactly to the pixel space?
So from the principal component space to the pixel space.
Yes.
That's what we're doing. If you apply the inverse transformation of PCA, it will bring you back to the random feature space, right?
And then from the random feature space, you go back to pixel space.
Yeah, that you could do. I don't know which one would be better actually. I never tried that one. Sounds like a good idea. Okay, so I have here to plot. Okay, call it that hat here. So let's see if this works out of the box. Okay, so you get something like this. It's not great, but we have reduced the digits to 20 numbers. So this is more drastic than most papers do. We can increase the dimensionality real quick and see what happens. The number of components. Sorry?
Can we compare the principal components of the transformed data and the original one to see like the reduction in errors or what we lose by doing the transformation to the random features?
Yeah, I think this is returned by randomized PCA. PCA dot explain variance. So you should from this. Yeah, so we're explaining a fourth of a variance. So let's take more. Let's take 50. And I will actually try your idea now to see.
What about the PCA around the syllable components of the original data set without mapping it to the random feature space?
Yeah, so that is much worse actually. You get much worse reconstructions. I didn't do that back in that exercise, but yeah, one of the points of this exercise was to show that by incorporating nonlinearity into the model, you get better reconstruction. So what we were proposed to map back to the random feature space, and I think we can do that by just the PCA inverse transform. Okay, yeah, that should do it. You get pretty much the same, I think. You get less parameters by progressing directly from the compressed space to the original space, but I don't think it's a big deal. Also, tuning the kernel, using multiple bandwidths, these things improve a lot the result for the sake of brevity. I just wanted to give you the flavor. Okay, and perhaps one last example that we could do is to build a little nonlinear correlation coefficient. Yeah.
I don't get where the information go from the PCS space to the pixel space without going by the kernel space.
It's just a regression, a linear regression here. So what you could do is, from the principal component space, you could apply a second layer of random features, and then do linear regression there. So then the function mapping the principal component space to the pixel space will be again nonlinear, and perhaps that would help. I have some examples in the slides that were done a bit of care. So these were test reconstructions for Cypher 10. They are a bit blurry, but I mean the method it's extremely simple, so it's actually surprising that it works to this extent. Anyway, as a last little thing, I want to show you how you can use random features to build a dependence measure. I think Arthur talked about a lot of kernel dependence measures. All of those share the same problems that kernels have, like you have to build the kernel matrix, you have to invert it, and so on. Well, using random features is also very, very simple to build a correlation coefficient for nonlinear patterns. And let's conclude with that, perhaps. So in order to do so, fresh start again. Okay, we will need our random features, of course. And then we will need to build some synthetic data. We can build a circle. So so if we plot this, should look like a circle more or less. Okay. And if we measure the correlation of this guy, I think we imported Pearson, yeah, X, Y. I think you have to return the first element of the matrix. You get the correlation of minus 0.04, right? So it's stupid to try to use a linear measure of dependence to measure the dependence in this circular pattern. So what can you do about it? Can you use kernels to develop a nonlinear test of dependence? I mean, this is a very basic problem that you will all find. You have two random variables and you want to measure to what extent they are dependent beyond correlation. So it would be actually very simple. It would be, once again, computing random features from a one-dimensional space. We don't need anything sophisticated here, so let's use 50 random features and then use rather small bandwidth. This will be a random feature generator for both x and y. Okay, so we have taken each of the points in the circle and we have mapped it to a 50-dimensional space. And now we want to measure, now we want to use a linear method on top of these random features that measures the correlation between z underscore x and z underscore y. So what linear method measures the correlation between two multidimensional random variables? Does anyone know? It's not PCA, but it sounds very similar. CCA, very good. So yeah, it's important. So we fit CCA on, sorry, yeah, fit on ZX and ZY. So it's going to be my CCA. And then I'm going to get the transformations, my CCA.transform. Set X. Oh, and we want just one component. They are sorted by correlation. We just want the first one. We just want the transformation that gets the maximum amount of correlation. So n components equals 1. Okay. So this should give me the, yeah. So this gives me the transformations. So fx should be one vector. Yeah, and then fy would be the same. So hopefully, CCA has been able to find the linear transformation of the 50-dimensional ZX data, and simultaneously a linear transformation of the 50-dimensional Z underscore Y data, such that these transformations are maximally correlated. So in other words, it has extracted the nonlinear dependence of the data using a linear method on top of the random features. Let's see if this is true. So we just plot this guy. Y with dots, and the circle has been warped into a thing that is pretty much correlated. We can check. So 88, 0.88, which is a rather large number when compared to 0.04.
So I'm confused.
Yeah.
If we do first random projections, right?
Yeah. So we got the circles, one dimensional, and we blow up each of them to a random feature space.
Right. So I'm not sure, like, if we would have like actually independent variables, if they wouldn't be able to find out on the same.
Yeah. So exactly. So if the question was, if the random variables were independent to begin with, will this random feature transformation find some kind of spurious correlation, right? And then tell you, hey, they are dependent when they are indeed not. And yeah, this is possible. This is just, yet again, another instantiation of overfitting. So then you will need to regularize CCA and the model selection. Yeah. And if you are curious, you can also plot the transformation that the model is learning. That is just x fx. And so if you get this circle and you apply this transformation to the x space, and this transformation here to the white space, then this circle gets magically arranged into this highly correlated structure. Okay? And I think we're 10 minutes away from finishing, so let's do a round of questions and finish it here. Yeah?
Sorry, I look at the kernel applied here is translation environment kernel?
Yeah. Yeah. So I generated random features using the approximation to the Gaussian kernel. So like this.
The kernel is not really randomized.
Sorry?
You said it's random features, but it's not really random. It's a translated environment kernel. I don't know if we don't have that.
It's a randomized approximation to a shift invariant kernel. So the features are random because I'm sampling the parameters from a distribution without looking at the data. Yeah. Yeah.
What other methods can we apply to large kernels?
Yeah, so I don't have time to go over the last example that I had, but I think Arthur talked about kernel mean embeddings, which is getting a distribution and mapping it to a reproducing kernel Hilbert space. What we did once with this is to get distributions of two random variables where either x causes y or y causes x. This is a very difficult problem to solve. There's no closed form expression or test to see when given two random variables which one is the cause and which one is the effect. So one way to go about this is to get the distribution, map it to a kernel, in this case with a bunch of random features. So you will get like this summary or footprint of the distribution as a fixed dimensional vector of random features, and then run a classifier through that. And the classifier will split +1 if x goes y or -1 if y goes x. So in order to learn from distributions, people use kernel mean embeddings, and in order to scale kernel mean embeddings, you can use random features. For example.
Are sketch methods for kernels worth exploring? Or is more like a theoretical?
Sketch methods like CUR decomposition and stuff like that. Yeah, I think people is actively working on that. You can, for example, Google names like Michael Mahoney in Berkeley or stuff like that. And one application, so when you hear about, so many times deep learning and stuff like that is really successful because of convolutions and stuff like that, right? It exploits the fact that we're dealing with images, so you convolve a kernel through the image. So that is a lot of prior knowledge embedded into the neural network. But when it comes to fully connected layers, it has been shown, for example, that if you replace the last fully connected layers in a neural network with a layer of random features, it works just as well. Right? So that's pretty cool also. There was another question somewhere.
No more questions. Let's thank the for this